Pick up a piece of paper, hold it above the floor and let it go. It falls. Simple. Gravity pulls it down. Now walk outside in a thunderstorm, look up at the sky, and watch electricity travel 10 kilometers to hit the ground. That falls too, in a way. But the mechanisms are so different, the scales so incomprehensible, that calling both of them things falling is like calling a whisper and a nuclear explosion, things making noise. Let me tell you what lightning actually is, because most explanations I've heard treat it like a mystery dressed up as an explanation. Opposite charges attract. Fine, yes, but why are there opposite charges in the first place, sitting up in a cloud 3 kilometers above your head, organized neatly enough to discharge in a single brilliant stroke? That's the part people skip over, and it's the most interesting part. Start with the cloud, not a puffy white decorative cloud, a cumulonimbus, the kind that's maybe 12 kilometers tall, churning internally like a pot of boiling water. Inside this thing, there's ice. Enormous quantities of ice crystals at the top, heavier graupel, half hail, half slush, lower down. The atmosphere is forcing warm, humid air upward at sometimes 150 kilometers per hour inside these updrafts. So the ice crystals are being hurled up while the heavier graupel falls or stays lower. They collide constantly, millions of collisions per second. Here is where the physics gets interesting and the standard explanation gets lazy. People say the collisions cause charge separation. True, but how? The mechanism is something called the non-inductive charging process, and it depends on temperature, on the size of the particles, and on whether there's supercooled liquid water present. When a small ice crystal collides with a larger graupel pellet in the presence of supercooled water, electrons transfer. The small crystal takes positive charge and gets swept upward by the updraft. The graupel retains negative charge and stays lower. Do this millions of times per second, and you get a massive charge separation. Positive region near the cloud top, negative region in the middle and base of the storm. The numbers get staggering fast. A single thunderstorm can accumulate charge differences of 100 million to 1 billion volts. Not between the cloud and the ground yet, just inside the cloud. Now the ground. Here's the piece that most explanations skip entirely or explain backwards. You might think the ground is neutral, passively waiting. It isn't. The ground is a conductor, and the negative charge at the base of the cloud induces a positive charge on the ground directly below. The cloud's negative charge repels electrons in the Earth's surface, pushing them away, leaving a positive region of ground right under the storm. So you have negative charge above, positive charge below, and a distance of maybe 2 or 3 kilometers between them. The potential difference across that gap can reach 300 million volts. For comparison, the outlet in your wall runs at 120 volts. We are talking about a factor of 2.5 million difference in voltage. Why doesn't it discharge immediately? Because air is normally an excellent insulator. Dry air at sea level will resist electrical breakdown up to about 3 million volts per meter. Across a kilometer of air, that's 3 billion volts before breakdown occurs spontaneously. The cloud is not reaching those voltages in most cases, so something else has to happen. What happens is extraordinary, and almost nobody explains it correctly. Lightning doesn't leap from cloud to ground in a single stroke, not at first. What actually happens begins with something called a stepped leader, an invisible, forking channel of ionized air that propagates downward from the cloud, not visible to your eye, not the bright flash you see. It moves in discrete steps, each maybe 50 meters long, pausing about 50 microseconds between each step. It's probing downward, following the path of least electrical resistance through the air, which is why lightning zigzags. The path isn't random chaos. It's the accumulated result of the leader finding slightly more conductive patches of air, patches where cosmic rays have already freed a few electrons, patches where the humidity is higher, patches where previous partial discharges have weakened the insulation. While this stepped leader is descending, taking maybe 20 to 50 milliseconds to cover a kilometer, something remarkable is happening from the ground up. Tall objects on the ground, trees, buildings, wet soil, people standing in fields begin emitting their own upward streamers. These are faint upward-reaching channels of ionized air, pushed up by the intensifying electric field as the stepped leader gets closer. Most streamers never connect to anything. They rise a meter, maybe 10 meters, then dissipate. But when the downward-moving stepped leader gets within 100 to 200 meters of the ground, one of those upward streamers connects. They meet, and the instant they connect, something called the return stroke fires, and this is what you actually see. The return stroke is a wave of electrical discharge that propagates back up the now complete ionized channel from ground to cloud at roughly 100,000 kilometers per second, 1/3 the speed of light. The current in that channel reaches 30,000 amperes on average. Some strokes hit 300,000 amperes. The temperature in the channel reaches 30,000 Kelvin. That's 5 times hotter than the surface of the sun. The air expands so violently, so rapidly, that it sends a supersonic shock wave outward. That's the thunder. Now, why does lightning strike the ground at all? Why not just discharge cloud to cloud? A lot of lightning does discharge cloud to cloud. About 75% of lightning discharges are intra-cloud or cloud to cloud. But the question is why ground strikes happen at all, since the shortest path is clearly not from cloud base to the surface of the Earth, which requires crossing kilometers of insulating air. The answer is that the ground is part of the circuit. The Earth, the whole spherical conductor of it, maintains a global electric circuit. In fair weather, the atmosphere carries a small downward current of about 1,000 amperes globally, tiny, spread over the entire planet. The ionosphere at 60 kilometers altitude carries positive charge. The surface carries negative. Thunderstorms are the generators that maintain this circuit, pumping charge up into the ionosphere continuously. Lightning strikes are literally part of the mechanism by which the atmosphere resets the charge distribution that fair weather slowly erodes. The planet needs the lightning. Without the roughly 100 lightning strikes occurring every second globally, the global electric circuit would discharge and equalize in about 10 minutes. So when lightning hits the ground, it isn't doing something anomalous. It's doing what the entire global electrical system requires it to do. Now I want to talk about why it hits that tree, that flagpole, that person on the golf course, rather than the flat field nearby. This is where the physics becomes directly, personally relevant to you. The stepped leader doesn't aim at tall objects. It doesn't know tall objects exist. What it does is propagate downward following the path of least electrical resistance. As it gets close to the ground, within that critical 100 to 200 meter range, the electric field at the tips of tall conductive objects is enormously enhanced. This is basic electrostatics. The electric field concentrates at sharp points and curved surfaces with small radii of curvature, at the tip of a metal rod or the branch of a tree, or, here's the uncomfortable part, at the top of your head, the electric field can be 10 to 100 times stronger than it would be at the flat ground beside you. This enhanced field is what drives the upward streamer. The taller and more conductive and more pointed the object, the more likely its streamer will be the one that connects to the descending stepped leader. A lightning rod works not primarily by attracting lightning in the Hollywood sense, but by reliably providing a well-grounded conductive path so that the inevitable connection happens there rather than somewhere arbitrary and undesirable. Benjamin Franklin figured out the basic principle in 1752, demonstrating with his kite experiment that lightning was electrical in nature. What he showed was that the storm clouds had the same properties as the friction-charged Leyden jars people were playing with in laboratories. They could make sparks, they attracted and repelled objects, they shared all the measurable properties of static electricity. This was not obvious before Franklin. Lightning was widely considered supernatural, or at minimum a force separate from anything humans had observed in their parlors and workshops. Franklin collapsed that distinction, and in doing so made the lightning rod possible. The physics of protection, the reason you're told not to stand under trees, comes directly from the mechanisms I've described. A tree struck by lightning carries 30,000 amperes through its wet, relatively conductive interior. The water in the tree flashes instantly to steam. The trunk explodes. Ground current radiates outward in all directions from the strike point for dozens of meters, and this ground current is what kills animals and people who are nearby but not directly struck. 2 legs apart on a conducting surface while ground current is flowing means your legs are at different voltages. That potential difference drives current through your body. Wide leg stance is more dangerous than feet together, which is why crouching low with feet together is the recommended posture if you're caught outside. There are things we know very precisely and things that remain genuinely open. We know the charge distributions inside storms to reasonable accuracy. We know the mechanism of stepped leaders and return strokes because we can photograph them with cameras running at millions of frames per second. and we can trigger lightning deliberately by firing rockets trailing copper wire into storms. We can measure the current, the temperature, the propagation speed. These numbers are solid. What we don't fully understand is the triggering, the exact conditions that initiate the very first discharge inside the cloud. Why here? Why now? Why this particular collision sequence crossed whatever threshold was needed? This is still a research problem. Cosmic rays may play a role. There's evidence that high-energy particles from outside the solar system can ionize enough air to seed the initial breakdown. The details of how the stepped leader chooses its path, the exact physics of the connections between downward leader and upward streamer, these are active areas of atmospheric physics with work being published right now. What you should carry away from this is something stranger and more beautiful than the simple picture. The lightning bolt you see in half a second has a history. Weeks of solar heating evaporating ocean water, days of a hurricane-seeded air mass traveling across a continent, hours of a storm system organizing itself, minutes of charge accumulation, milliseconds of an invisible stepped leader probing downward, and then the return stroke, the visible part, lasting 0.2 milliseconds, the bright flash, 5 times the temperature of the sun for 1/5 of a millisecond, and then it does it again. The same channel, still partially ionized, can carry 3, 4, sometimes 20 return strokes in the 200 milliseconds following the first. That's the flickering you see in longer lightning bolts. Not one stroke, but many, reusing the same channel as long as it stays conductive enough to connect. The Earth runs on this. The whole global electrical circuit, the one that makes the ionosphere positive and the surface negative and the fair weather electric field everywhere around you point downward at 100 volts per meter. You're sitting right now in an electric field of 100 volts per meter, and you don't feel it because your body is a conductor and the field inside you is 0. The thunderstorms, all 2,000 of them going simultaneously at any moment across the planet, are the generators. The lightning is the current return path. It has been running like this for at least 3.5 billion years since liquid water and weather systems first existed on this planet. The next time you see lightning, you're not watching a dramatic accident of atmospheric electricity. You're watching the power supply for the global electric circuit complete its cycle. You're watching the sky pay its electrical debt to the ground. That is not a metaphor. That is the mechanism.